Now we'll discuss the working principle of a three-phase induction motor. So if you remember, any motor, maybe a DC motor or a induction motor or a synchronous motor, they works on the principle of Lorentz law. So what is that Lorentz law says that in mathematical form I can write F is equal to B I L. So what is the text statement for this Lorentz law? If I am having a magnetic field B and if I am having a conductor of finite length L, and if this conductor is carrying a current I, and if this current carrying conductor is placed under a magnetic field, the conductors will experience a force, and because of that force the rotor starts rotating. So the simple text statement for that Lorentz law is that if a current carrying conductor is placed under a magnetic field, the conductor will experience a force, right? So let me write that statement. What is it? If the current carrying conductor is placed under a magnetic field, it experiences a force. Let us see in case of a induction motor how these three conditions are being satisfied. What are those three conditions? One is the magnetic field B. The second one is the conductors of finite length L. Third one is how the conductors are made to carry current. So we are trying to discuss from the basic level, or I mean to say the ground level. Let us see one by one. If you see in case of a three-phase induction motor, if you remember, I will be having a stator. And in the stator, we will be placing or will be distributing the conductors of a three-phase windings with a space angle of 120 degrees. For explanatory purpose, let us consider there are some conductors of the three-phase windings which are distributed in the stator slots. And these conductors are being joined to form a three-phase windings, and the similar ends or the dissimilar ends of the windings are being joined together, and the remaining terminals are being brought out, right? So let us consider the three terminals of those three-phase windings are brought out, A, B and C. Let us consider each phase is wound for 4 poles. Each phase is wound for 4 poles, or each winding is wound for 4 poles, right? So the stator carries a three-phase windings, and these three-phase windings are physically spaced at an angle of 120 degrees, and the three terminals of those three-phase windings are brought out. Let us consider for our explanation purpose or explanatory purpose, those three-phase windings are wound for 4 poles per phase. Now, to these three-phase windings, when I give a three-phase supply, which is IA, IB, IC, let the frequency of those three-phase supply be 50 Hz. Then very immediately, what are formed in the stator core? Magnetic poles. So I think we will be having a detailed discussion in our regular video classes how the poles are formed in the stator core. We will have a detailed discussion. So, being an electrical engineer, so to understand the working principle, you should know how the poles are formed in the stator core. But we cannot see, but mathematically we can prove that the poles are formed. So, whenever we are having poles, definitely we will be having magnetic flux lines. Magnetic flux lines. So, remember, for our convenience purpose, I am showing only the north pole here. So, remember, only north pole alone cannot form. On the opposite side, there will be a south pole. So, here, due to the space restriction, I am not drawing the south pole. Imagine there is one more pole, that is the south pole on the opposite direction. On the direction of this magnetic flux lines are from north to south like this, and internally south to north, right, like this. So, poles are formed. So, whenever a three-phase supply is given to the three-phase winding, what are formed in the stator core? Magnetic poles, right. What is the nature of these poles? Means the nature of these poles which are formed are rotating. So, if I am trying to show something like animation, these poles which are formed in the stator core will be rotating. So, these are rotating like this, When these poles are rotating, what happened to these magnetic flux lines also? They will also rotate. So, with the poles, they will also rotate. So, if I am trying to mix up these two, so maybe difficult, we will try. So, these poles, as these poles are rotating, the flux lines are also rotating. You can see the flux lines are also rotating. You can see. So, I cannot select the arrows, but imagine the arrows will also rotate. Please remember. So, the nature of poles are rotating, right. So, whenever a three-phase supply is given to the stator winding, what are formed in the stator core? Magnetic poles. And what is the nature of those poles? Rotating. As the poles are rotating, the group of flux lines, that is the flux, is also rotating, and I am naming that flux as stator flux. Why I am naming it as a stator flux means those flux lines are due to the stator poles or the poles, and those poles are because of the stator windings and stator currents. So, that is the reason I am calling it as a stator flux. Then what is the speed at which these flux lines will be rotating? Means they will rotate with the same speed as the poles. Why? Because we have seen. So, here whatever the speed the poles are rotating, whatever the speed the poles are rotating, the flux lines are also rotating. So, what is the speed at which those poles will be rotating? Means those poles will be rotating with a speed of ns, and the flux lines and the group of flux and the flux is also rotating with a speed ns. So, what is the first observation we can see here? The speed of the stator field with respect to the stator will be ns. So, if I am calling the stator as a stationary observer, then what is the speed of the poles with respect to the stationary observer? Means ns. So, the stator field is rotating with the stator with a speed equal to ns. So, I will be writing that point, that is the speed of stator field with respect to the stationary observer. Here the stationary observer is nothing but the stator. Stationary observer is ns. Right. So, what is the first point? So, whenever we are giving a three-phase supply to the stator winding, what are formed in the stator core? Magnetic poles. What is the nature of those poles? Rotating, and the flux lines are also rotating, and the group of flux lines, that is the flux, is also rotating. So, this is a very, very important question. Many times this was asked. This question will be like this. Let us assume that you are standing on the stator core, or you are standing on the stator core surface. then for you, what is the speed of the stator poles or the stator field? So the speed of the stator poles or the stator field is nothing but ns. Now if I want to correlate with this, your Lorentz law, as the Lorentz law says that for a mechanical force, I need to have magnetic field B. So in order to meet the first requirement B, that is the magnetic field or the magnetic flux density, whatever it may be, I am using the term magnetic field in order to produce the magnetic field in case of a induction motor. So how we are going to meet that requirement means we are taking a three-phase windings, and we are passing three-phase currents. So whenever we are passing three-phase currents into the three-phase windings, so what are formed in the stator core? Magnetic poles. And what is the nature of those poles? Rotating. As the poles are rotating, the flux lines will also rotate, right? Done. So now I need to know what is the speed at which that poles will be rotating. So the poles will be rotating with a speed of ns, which is given by 120 into f by p. So in this case 120 into 50 by 4. So in this case the speed of the poles is 1500 rpm. 1500 rpm. So what is the speed at which the poles are rotating inside the stator core means 1500 revolutions per minute. So they are making 1500 revolutions per minute, right? Done. Now if you remember, according to the Faraday's law, whenever there exists a relative speed or relative motion between the magnetic flux and the conductors, an EMF will be induced. Now if you look into these stator conductors, so these are the stator conductors which are placed in the stator slots. You can see the circle means inside that we are having stator conductors. So these stator conductors are stationary and the stator field in the air gap is rotating. So there exists a relative speed between the field and the stator conductor. The field is rotating with a speed of ns and the stator conductors are stationary. So there exists a relative speed of ns between the stator field and the stator conductors. Once again, according to the Faraday's law, whenever there exists a relative speed or relative motion between the flux and the conductors, what is induced in the conductors? An EMF is induced. Now if you look here, the stator conductors are stationary and the field is rotating. As the field is rotating with a speed of ns, as the stator conductors are stationary, there exists a relative speed of ns between the stator field and the stator conductors. So due to which there exists a relative speed, there is a EMF induced. In other way, if I am assuming these are the stator conductors which are in the stator slots, and these are your stator flux lines. As the stator poles are rotating, the flux lines are also rotating. As the flux lines are rotating, they are cutting the stationary stator conductors. So the stator conductors are cut by the rotating stator flux lines. So due to that flux cutting, what is induced in the stator conductors means an EMF is induced in the stator conductors. So can I mix up these two? Can I give a consolidated statement? That is, whenever there exists a relative speed between the flux and the conductors are winding, then the flux lines will be cutting the conductors. So whenever the flux lines are cutting the conductors, according to Faraday's law, what is induced in the conductors? An EMF is induced in the conductors. So here the stator flux lines are rotating, the stator conductors are stationary. So these rotating flux lines are cutting the stator conductors. So due to this flux cutting, an EMF is induced in the stator conductors according to Faraday's law, right? So I'll give the statement. Due to the relative speed, between the stator flux and the stator conductors, stator conductors, stator flux lines, stator flux lines are cutting the stator conductors. As a result, an EMF is induced in the stator windings. According to Faraday's law. Let me just go through the statement. Due to the relative speed between the stator flux and the stator conductors, stator flux lines are cutting the stator conductors. As a result, an EMF is induced in the stator windings according to Faraday's law. Then if I want to find out the magnitude, so it is nothing but the AC machine's voltage 4.44 F1, Phi1, N1 and the winding factor. So in this, F1 is the frequency of induced EMF in the stator windings. So this depends on relative speed into poles by 120. So relative speed means which field is responsible for this EMF? Stator field, right Baba? Stator field. So what is the speed at which that field is rotating? ENS. And in which conductors it is induced? Stator conductors. What is the speed at which the stator conductors are there? Zero speed. So can I say relative speed is nothing but the speed of stator field which is responsible for the EMF and the speed of the stator conductors in which an EMF is induced. So I need to find out the speed at which the stator field is rotating and the speed at which the stator conductors are rotating. So what is the speed of the stator field? It is Ns minus the speed of the stator conductors is 0 into P by 120. So it is nothing but Ns into P by 120. If I substitute in our case 1500 into 4 by 120, if I solve this, it will be 50 Hertz, which is nothing but F frequency. So the frequencies of the stator EMF is always equal to the supply frequency. The second observation in the working principle is, what is the frequencies of the induced EMFs in the stator windings? So the frequencies of induced EMFs in the stator windings is always equal to the supply frequency. Why? The stator conductors are stationary and the field is rotating with a speed of Ns. Then what is the relative speed between the stator conductors and the stator field? Ns. And hence the frequency of the induced EMF will be the supply frequency. For example, say the supply frequency is 50 Hertz and the poles are 4. Then what is the relative speed between these two? 1500. Then what is the frequency of the stator EMF? 50 Hertz. Say you are changing the supply frequency to 25 Hertz. Let us say. Then the field becomes 750 RPM, the relative speed becomes 750 RPM. Even the frequencies of induced EMFs in the stator windings again becomes 25. So always the frequencies of induced EMFs in the stator windings will be equal to the supply frequency. Whenever you are changing the stator whenever you are changing the supply frequency, the synchronous speed will change, then the relative speed will change, and proportionately the frequency of the stator will also change, stator EMF will also change, so which is always equal to the supply frequency. So there is no doubt that the frequency of the stator EMF will be always equal to the supply frequency. So why? Because when F is the supply frequency, Ns is the field speed, then the relative speed is Ns, then the frequency of the stator EMF will be F. When you are changing the supply frequency to F by 2, the synchronous speed will change to Ns by 2, then the relative speed will change to Ns by 2. Again, the frequency of the stator EMF becomes F by 2. So always the supply frequency and the stator frequencies of EMF will be, or the EMF, stator EMF will have the same frequencies, right? So this is the second point. So this EMF, even we call it as a back EMF. Back EMF. This is a back EMF. This back EMF is playing a very important role in motors. Very important roles in the motors. So without a back EMF, there is no motoring at all. So back EMF is required for motoring. So why the back EMF is required, we'll see. But before to that, I'll try to cut short in case of a DC motor, what is the role of a back EMF, right? So if you remember, IA is equal to V minus EB by RA, right? This is the armature current equation for the DC machines, right? Done. So whenever the load on the motor is increased, then immediately what happened to the armature speed? Decreases. What happened to the back EMF? Decreases. When the back EMF decreases, this difference will increases, then this current will increase, voltage into current, the power will increase, then the power fed to the armature will increase, then the mechanical power increases, and the torque supplied to the motor the load will increase. Why? Because, so whenever the load torque is increased, the motor torque has to increase. For increasing the motor torque, the armature should receive more power. For that, it should have more current. So how the things are happening means, whenever you are increasing the load, the speed decreases. When the speed decreases, the back EMF decreases. When the back EMF decreases, V minus E will increases. The current drawn will increase, the power drawn will increase, and the power fed to the armature will increase. The mechanical power, the torque will increase. Like that, with the increase in load torque, the motor torque also increases. So who is going to balance the power? Means the back EMF. Why? The load is a mechanical load. So whenever you are changing, this electrical parameter E is changing, and proportionately IA is changing, and the power drawn will be changing. So that is the reason a back EMF is very important in case of motors. So similarly here, even in case of induction, we'll try to understand the role of E, the back EMF, how it is important in case of motoring. But as of now, we'll see this. So here, E1 is the back EMF, or in other way, the EMF induced in the stator winding. So EMF induced in the stator winding. EMF induced in the stator windings. Stator windings. So what is the second observation we can see? The frequency of induced EMF. The frequency of induced EMF induced EMF is always equal to induced EMF in stator windings. In stator windings is always equal to supply frequency. Supply frequency. Supply frequency. Right? This is the second point. Right? Done. Now, if I look into this construction, so on the upper side we'll be having the stator conductors. Now in the air gap, so below to that we'll be having the rotor, and on that there will be rotor conductors. So these are the rotor conductors of finite length L, right? So again, if I go back to your Lorentz law, what is that Lorentz law says that for force on the conductors, I need the magnetism. So in order to meet the first condition, we have taken a three-phase windings and three-phase current, and we can produce a magnetic field which is rotating and whose magnitude is constant, right? The next one is I need a conductors of finite length L. So where we are placing those conductors of finite length L? On the rotor core in the rotor slots. The second condition is also over. What is the last condition? This rotor conductors has to carry some current. But we are not using any external source to supply the current, but the currents will be induced. How the currents will be induced means, let me continue. Now again come back. So as these poles are rotating, flux lines are rotating. As the flux lines are rotating, they are cutting the stator conductors. So they are not only cutting the stator conductors, even they are cutting the rotor conductors also. Why? Because as of now rotor is stationary, so these are the rotor conductors if I am assuming, on the above stator conductors. So these are, so if I am just looking here, so this black color is assuming the stator conductors and the white color is assuming the rotor conductors. As the flux lines are moving, so they are cutting the stator conductors, also the rotor conductors. So because of the flux cutting, what is induced in the rotor conductors? Also EMF, right? Why? Because as of now rotor is stationary, rotor conductors are stationary, but this field is rotating. So due to the relative speed between the field and the rotor conductor, so even the stator flux lines are cutting the rotor conductors also. So due to this flux cutting, what is induced in the rotor conductors? EMF is induced. Again, which law? Faraday's law. I'll repeat that statement. Again, due to the relative speed, between the stator flux lines and the rotor conductors, the stator flux lines are cutting the rotor conductors, as a result an EMF is induced in the rotor conductors according to Faraday's law. Let me once again read the statement. Due to the relative speed between the stator flux lines and the rotor conductors, the stator flux lines are cutting the rotor conductors. As a result, an EMF is induced in the rotor conductors. I'll try to write that equation. So E for the voltage, 2 for the rotor side. In addition to that, I am writing 0. So 0 means when the rotor speed is 0. So here E2 naught means the rotor voltage at standstill. So this is equal to 4.44 F2 phi1 N2 Kw2. Please remember, this is not a printing mistake. So which is the flux as of now cutting the rotor conductors? Phi1. That is the reason I wrote phi1. So here phi1 is the flux which is cutting the rotor conductors, and F2 is the rotor frequency. So if I write F2 is the rotor frequency, again it depends upon relative speed into poles by 120. Again, which field is cutting the conductors? Stator field. What is the speed at which it is rotating? Ns. So to which conductors it is cutting now? Rotor conductors. As of now, what is the rotor speed? 0 into P by 120. If I substitute, it is Ns into P by 120. So Ns into P by 120 is nothing but F. Then the frequencies of the rotor currents will be the supply at starting. So the next observation and very, very important observation is what is the frequencies of the rotor currents at starting. So the frequencies of the rotor currents or the rotor EMF at starting will be equal to the supply frequency, right? So once again, as of now, the rotor is stationary. The rotor conductors are stationary, the rotor field is also, the rotor core is also stationary. But in the air, the flux lines are rotating, right? So which one is rotating now? Flux lines. As these flux lines are rotating, they are cutting the rotor conductors. So due to this flux cutting, what is induced in the rotor conductors also? EMF. And what is the frequency of that induced EMF? Supply frequency, right? So can I say the frequency of induced EMF in the rotor windings at starting is equal to the supply frequency, right? So I hope it is the second observation, right? Now I want to know the direction of induced EMF. You can see here, so due to the flux cutting, an EMF is induced in the rotor conductors. It is true. I want to know the direction of induced EMF. If I am assuming this one as the rotor conductor, so the flow of current is into or outwards. So that EMF will make the current to flow inside the bars or outside the bars. I want to know. So if I want to know that, I'll be using Fleming's right hand rule. So what is that Fleming's right hand rule? Says that if you want to know the direction of induced EMF in a particular conductor, then with respect to that conductor, find out the direction of the flux lines, find out in which direction the conductor is moving, then the middle finger will give the direction of induced EMF. The text statement for Fleming's right hand rule is, right hand rule is stretch the first three fingers mutually perpendicular of your right hand, place the forefinger in the direction of field, thumb in the direction of motion of the conductor, then the middle finger gives the direction of induced EMF, right? So let us consider one conductor here to know the direction of induced EMF. I'll call this conductor as A. So with respect to that conductor A, I want to know whether the direction of current is inwards or outwards. So for that, let me zoom that conductor A. I want to know the direction of flux lines. So in which direction the flux lines are there? You can see the flux lines are downwards. So the first condition I am able to understand. What is the first condition? The direction of magnetic field, right? Done. The second one is in which direction the conductors are moving. But here the conductors are not moving, the field is moving. So here two things. See, if I am assuming these are my four fingers representing the flux lines and this is my conductor, rotor or any conductor. So for example, if I am moving the conductor, so this moving conductor is cutting the stationary flux lines. So this conductor is cutting the stationary flux line. As a result, what is induced in this conductor? EMF. That is one possibility. The second case is the conductor is stationary but the flux lines are moving. In the second case, the moving flux lines are cutting the stationary conductors. So once again I'll come back. So here the flux lines are stationary. First case, the conductor is moving. So moving conductor is cutting the stationary flux lines. Let us consider the second case. The conductor is stationary but the flux lines are moving. In the second case, the moving flux lines are cutting the stationary conductors. So in both the cases an EMF will be induced. So this case comes under the second one. So which one? So the rotor conductor is stationary but the flux is rotating. The flux is moving. Right? So as the flux is moving, the conductors are stationary, the moving flux lines are cutting the stationary conductors. As a result, what is induced here? An EMF is induced. But if I want to apply the Fleming's right hand rule, the conductor should be moving, but here the conductors are stationary. Then how to apply Fleming's right hand rule? Can we apply here? Absolutely we can apply here. But how to apply here means, before I try to apply, I'll give a small example so that you can understand more clearly on this. Say you are sitting in one bus, right? And bus is stationary and you are sitting in that bus. So next to you there is one more bus standing. Both the buses are standing and you are in the bus station, right? Both the buses are standing, they are stationary, they are not moving, they are stationary. So during that time, what you are trying to do means you are trying to operate your mobile, playing with your mobile. So during that time, what has happened is the bus which is next to you, say is moving in forward direction. Then if you see the bus at that instant, you feel that you are moving in opposite direction. But truly speaking, you are stationary, but because of an illusion for that instant, you feel that your bus is moving in opposite direction. Why? Because the bus which is there in the next, you feel that it is stationary and you are moving in opposite direction. But it is wrong. That fact is the bus which is moving in next to you is moving in forward direction, but you are stationary. So I think you might have experienced this. So here also I'll apply the same logic. What is that? If I want to know the direction of induced EMF, I'll assume that these conductors are moving in a direction opposite to that field. Taking the field as a stationary, and I'll assume that the conductors are moving in opposite direction. Right? So here Fleming's right hand rule can be applied, but here the conductors are stationary but the field is moving. So whatever that Fleming's right hand rule you have learned in your graduation or in your BTech, so it is with respect to moving conductors. So the thumb says that the conductor should be moving, but here the conductors are stationary but the field is moving. So to apply the Fleming's right hand rule, we have to assume that the conductors are moving in a opposite direction. So in which direction the field is moving? Clockwise. Then I'll assume that the conductors are moving in counterclockwise direction. But the fact is the conductors are stationary but only the field is moving. But to apply the Fleming's right hand rule, we are assuming that the conductors are moving in opposite direction. So here you can see the conductors are assumed to be moving in opposite direction. You can see field is downwards. The conductors are assumed to be moving in counterclockwise direction. Then you can see the middle finger of my hand is coming out. Means it is like this. It is like this. So what will be the direction of induced EMF? Means it is dot. It is dot. It is dot. Dot, right? So here you can see the direction of induced EMF will be dot, right? Done. Then as I told you that, so as you are aware that, so here the rotor bars are closed. So if you just look into a small example, if I am having a battery, and if I am closing this battery with some load, then this battery will supply the current. The battery will supply the current. So here also in case of a induction motor, the rotor circuit is closed. The rotor circuit is closed. Right? 1 second, Baba. Right. The rotor circuit is closed. Then whatever the EMF that is induced will circulate a current. And you can see these are the rotor conductors carrying current and they are under magnetic field. And hence the rotor conductors will experience a force. So on which principle this is working means Lorentz law. So if you want to have a mechanical force or force on the conductors, what are the conditions you need to satisfy? So those conditions are F is equal to BIL. So the first condition is B, which we are trying to produce using a 3-phase windings and 3-phase currents. The nature of the field is rotating. The second one is I need a conductor of finite length L. So where we are placing those conductors of finite length L? In the rotating part called as a rotor and in the rotor slots. And what is the third condition? The rotor conductors has to carry a current. But for that, we are not using any external source to supply the current. We are not using any supply to supply the current. But whatever the current that circulate will be because of induction or induced current. How? As the poles are rotating, the stator poles are rotating, you can see they are cutting the rotor conductors, EMF is induced. As the rotor circuit is closed, the induced EMF is circulating a current, so that current is a induced current. So Lorentz never said it should be a conduction current or some current, it should be a current. So this current is a induced current. Induced current. Induced current. You can see this is the conductor which is carrying this current I. The current carrying conductors are placed under a magnetic field, and hence the conductors will experience as a force. Now I want to know in which direction the rotor rotates. Right? So for that I have to use Lenz's law. So what is that? Lenz's law says that the effect should oppose the cause. So it is very similar to your Newton's third law. What is that? Newton's third law says that for every action there is an equal and opposite reaction. So here also the effect should oppose the cause for that. So let us see in which direction the rotor rotates. Whether the rotor rotates in the same direction as the field, clockwise, or the rotor rotates in a direction opposite to the field, that is counterclockwise direction. So for that I will be using Lenz's law. Right? So what is that? Lenz's law says that? Lenz's law says that the effect should oppose the cause. The effect should oppose the cause. So we'll try to identify what is the effect and what is the cause for that. Right? So what is the effect and what is the cause for that? Right? We'll try to see what is the effect and what is the cause. Now the rotor is a stationary person. So the rotor as of now, he is stationary. Stationary. The rotor is as lazy as you and me, always want to sleep. The rotor is sleeping, snoring. Let me explain what is that effect and what is the cause. The rotor is sleeping, means the rotor is stationary. Now let us say we have given a three-phase supply to the stator. Rotor is sleeping. Then when I give a three-phase supply, currents are flowing in the stator conductor. Rotor is sleeping. So those windings and those currents are forming the poles. Rotor is sleeping. And those poles are rotating, and the flux lines produced by those poles are also rotating. Rotor is sleeping. And those flux lines are cutting the rotor conductors. EMF is induced. Rotor is sleeping. As the rotor circuit is closed, the induced EMFs are establishing a current. Rotor is sleeping. And as the current carrying conductors are placed under the magnetic field, the rotor conductors are experiencing the force. As the rotor conductors are experiencing the force, they want to fly in the magnetic field. They want to fly in the magnetic field. The rotor conductors are locked inside the rotor slots as they cannot fly in the magnetic field. They are asking the rotor, "Arey chhod na." They are asking the rotor, "Please leave. We want to move. We want to fly. Please move." The rotor wakes up. "Arey, what is happening? Someone is trying to make me to rotate. Someone is trying to have a force." So the rotor rotates. So what is the effect? Means the rotor has to turn. Why? Because the conductors are experiencing the force, the rotor has to turn. So the turning effect, the twisting effect is nothing but the torque. So what is the effect? Means the torque. So the effect means the torque. So whenever you are giving a three-phase supply, the rotor is experiencing a torque. So the effect is the torque. Now the rotor wakes up. What has happened? Why I should turn? Then the rotor start diagonizing. What is that? Why the rotor conductors are experiencing the force? Why? Because the rotor observes that the rotor conductors are carrying a current. How the currents are flowing? Why? Because there is some EMF induced in the rotor current. How there is an EMF? The rotor circuit is not separately excited. Why there is an EMF? Why? Because the rotor conductors are cut by the flux lines. Which flux lines are cutting? Oh, stator flux lines are cutting. Why the stator flux lines are cutting? As the stator poles are rotating, the rotor is stationary. Because of the relative speed, the flux lines are cutting the rotor conductor. So who is the main cause? Means the relative speed between the stator flux and the rotor conductors. Because of the relative speed, the flux lines are cutting the rotor conductors, right? So what is the cause? Means the relative speed. Relative speed between the stator flux and rotor conductors, right? Now again the rotor has to sleep. If the rotor has to sleep, there should not be any torque. For no torque, the rotor conductor should not carry any current. For no current, the rotor conductor should not have any EMF. For no EMF, the rotor conductor should not cut by the flux lines. For no flux cutting, the relative speed has to be 0. So to make the relative speed 0, so in which direction the rotor rotates means it will rotate in the same direction. Right? So to obey Lenz's law, to make the relative speed between the stator poles and the rotor conductor, the rotor has to rotate in the same direction. I'll give a small example. Say it is a chilled winter, assume that December month, you are sleeping. One of your friend came with a glass of water which is kept in the refrigerator overnight, chilled water, and he poured that water on your face.